Okay. All right, let's get started. So a little bit on the housekeeping side of things. So the attendance grade should be up to date on Blackboard, although I have that note here, and I'm not sure if I posted the ones from last Friday, but if not, I will, because I'll post those and then the ones from today so that you'll have an accurate attendance grade before your celebration on Wednesday. For homework grading, I'd say I want to let you know everything up to 2.6 has been graded. Homework 2.7 is being graded, but the solution is posted. So I hope to for the TAs to be able to get that graded between now and Wednesday, but if not, you have the solution to that homework available to you as you prepare for the exam. I did assign homework 3.1 last week, but it is not due until next Friday. I think there's a few of you that went ahead and already did it, which is completely fine, but I didn't want you to have a looming homework assignment before the exam. Like I wanted to sort of spend this week, today and up through Wednesday, focus on the exam. In terms of the exam, I didn't put it here on this slide, but I usually make sure everybody's aware of the grade distribution. So the exams, each of them are worth 15%. And so the idea is so that no one exam really has that much of a big impact on the overall grade, but they're important enough that they ultimately matter. Any questions on logistics before we get into the exam review? All right. Get it? You get it? Okay. All right. All right. So let's go to. Where's my mouse? There we go. All right. Let's get into the exam review. And so what I've done here in this presentation is three things. So the first thing I'm going to do is I'm going to discuss the logistics for the exam. So in terms of format, what you can expect in terms of the types of questions. I'm going to go over the specific topics you will be examined on. And then there are slides at the end that are sort of a greatest hits of, as it were, of the presentations that I've had during the last few lectures. So the idea is that as you're preparing your formula sheet, this can at least be a starting point for developing a lot of that content. Okay, and again, all the lecture notes are on Blackboard, including this one, so you'll have this available. Okay, so let's talk about the logistics. And so this is how the exam is going to be operated, what's the approved material, what you can expect, so on and so forth. Okay, so the exam is going to be paper-based. In other words, I'm not sure if you have classes that are still doing exams through Blackboard, but we're going to do it in here on paper. One thing I do want to make sure is crystal clear. I do not intend for my exams to be time critical. So what I mean by that is I built this exam and then I took it, okay? And so the idea is that I took 50 minutes, divided it by 3, and the idea is I needed to be able to do the exam in that time frame. And if not, then I needed to pare the exam down. And I was able to do the exam in a little under 15 minutes. So that means you should have more than enough time to do the exam. The exam is going to be comprised of here's going to be the format. So there's going to be 4 to 5, turn that off. There's going to be 4 to 5 conceptual questions. Short answer questions, and then 2 to 3 computational problems. When I say short answer, I mean short answer, okay? One of the things I found, and this is sort of a piece of advice, is I have found sometimes in my classes that I have these short answer problems, and I look and I get sort of these Shakespearean sonnets that are like paragraphs and paragraphs of responses for a question that's worth 3 points, and then the questions that are worth 30 points, the students are scrambling through them, and so I really want to emphasize time management. If you are, so to put this in perspective, I want to tell you how I actually come up with point weights on problems. So I don't know if any of you watch speed running on Twitch, but I will actually pull out a timer and take each question and time how long it takes me to do the question, and then I will map that to a 100-point distribution, and that's how much the problems are weighted. So the idea is that if it takes me 30% of my time to do problem 2, well, then problem 2 needs to be worth 30 points, okay? So I do that not only to develop a fair means of assigning point weights to problems, but more so as a guide for you, okay? If you're taking half an hour on a problem that's worth 3 points, you're doing something wrong, okay? So I want to make sure that you're aware of that. So again, problem one, if you will, problem one is a series of short answer questions, number them 4 to 5, and then 2 to 3 computational problems. Those are the ones that are more akin to example problems in class and homework assignments and things like that. The exam is closed book, closed notes, but you are allowed a formula sheet, you are allowed a calculator. It's probably not the worst idea to bring a straight edge. You know, I don't know if you have like your student ID or something that can draw a straight line. I will admit, this probably doesn't matter a whole bunch for this exam, but there are some exams later where having a straight edge really would help, particularly exam 3, when we start drawing shear and moment diagrams and we start drawing, doing truss analysis and things like that, that having a straight edge really can make your life a little easier. Now, in terms of the formula sheet, this is an 8.5 by 11, both sides, front and back. You can put whatever you want on it with the following stipulations. Okay, I want you to put your name on it because I'm going to collect them after the exam. Okay, I ask that you don't put any fully worked out example problems. That is not for some stipulation that I'm trying to be a jerk for you. That truly is for your benefit, and I'll give you a perfect example of that. So let's say that you have a force on a homework problem that was, I don't know, at a 3 to 4 slope ratio, and then the exam problem has a 1 to 2 slope ratio. Suddenly you're doing the exam problem and you're pulling numbers from your formula sheet, and now there's 3 to 4 slope ratios that showed up on an exam problem that had nothing to do with the problem, right? So what ends up happening is it ends up creating more confusion for you as a student. I have seen that happen a lot when I sort of said, you know, whatever on the formula sheets. So I don't think that fully worked out problems on the formula sheet really helps you out. I actually think it hinders you, which is why I'm asking that you don't do that. The last thing is that the formula sheet needs to be prepared by you. In other words, like, I'm fine if you handwrite it. I'm fine if you word process it. I'm fine if you take an image here and there from a PowerPoint and snip it out into your formula sheet. Like if there's some figure that really explains things very well, that's fine. But what I don't think is a good idea is to just take the PowerPoint, copy and paste the whole thing onto an 8.5 by 11 and hit print. I don't think that's an adequate use of your time in actually studying. I actually think that crafting and creating the formula sheet is studying. Okay, that by going through and organizing your thoughts and putting them on paper, I think that's actually the study process. And when I say it needs to be made by you, it needs to be made by you. What I don't want to see is 12 formula sheets that are all the same because somebody made a really good one. And hey, can I copy that? No, I want everybody to make their own. So I think that will ultimately result in higher class averages for everybody here because, again, you've gone through the process and studied. In terms of the topics on the exam, so what we're going to be covering is everything through lecture 10. Okay, so this is the fundamentals and the particle static stuff that we talked about really for the bulk of the early part of the semester. So in terms of the fundamentals, you need to understand Newton's 3 laws of motion, or the classical motion and Newton's 3 laws. Make sure that you know how to compute the weight of an object. So if I give you the mass of an object, make sure that you can convert that into a weight. Make sure that you can convert units and perform dimensional analysis as appropriate, although I'll go ahead and tell you that I don't think that's going to be a heavy component of the exam. Really, the bulk of the exam is going to be on particle statics. But I do think you need to be able to employ concepts, and particularly algebra and trigonometry, and I think that's fair to say that that is going to show up in the main body of the exam, because we've been doing that for the past 6 or 7 lectures. In terms of the statics of particles, which is really the star of the show, so make sure that you understand the properties of vectors, how they're added, commutativity, magnitude and direction, things like that. Make sure that you can add vectors using graphical or trigonometric approaches, bless you, as well as addition by vector components, that's I, J, K, bless you again. And then make sure that you can apply equations of static equilibrium to solve concurrent force systems, that's forces all meeting at a common point, in both 2D and 3D scenarios. So what that also means is that you need to be able to solve 2x2 and 3x3 systems of equations. Again, something that is primarily handled by an adequate scientific or graphing calculator, but you do need to be able to do that because that's going to happen on the exam. The remaining part of the slides are, again, I'm trying to give you a starting point for developing a formula sheet. And I'd argue that most of what needs to go on your formula sheet you could probably find in these slides in terms of equations and data and whatnot. So first off, I've got a slide on fundamental equations and concepts. So first off, we've got that the relationship between weight and mass, and that's the acceleration due to gravity. So I have that in both SI and US units. I have, excuse me, our fundamental units in both SI and US units. And then, we have our relationship for our Newton and our relationship for our slug. I have here sort of a slide on trig. So this is sine, cosine, tangent. So this first box is just sort of the basics of right triangles, Sokotoa, and then the Pythagorean theorem. This box is for converting from rectangular to polar coordinates, which I would argue is really important when you're taking a vector and expressing it in IJ notation in 2D. And then the law of sines and the law of cosines, which we used early in the semester to solve problems where we had vectors, where we had two vectors applied at a given point and we needed to determine the resultant. In terms of IJ notation or IJK notation, this sort of leads into the basics of vectors. So the first is the concept of commutativity. So that means that we're graphically adding vectors in that tip to tail fashion. But what we learned based off of this graphical observation is that vector addition is commutative. So that means that the order of operations doesn't matter. A plus B equals B plus A, or P plus Q equals Q plus B. We have the definitions of our three essential basis vectors, IJK. So IJK are unit vectors. So remember, a unit vector is a vector with a magnitude of 1. The I vector points in the positive x direction. The j vector points in the positive y direction, and the k vector points in the positive z direction. And so what we can do is we can take any arbitrary vector pointing in any direction in 2D or 3D space and just say it's so much I, so much j, and so much k. So we can express vectors in a consistent format. So that's where IJK became so powerful. This is our means of taking an arbitrary vector and resolving it into a two-dimensional algebraic IJ expression. And as you know, we can do similar operations in 3 dimensions as well. And then I would argue probably one of the most bulky, but really, hey, here it is, summary tables that really sort of sets the stage for everything that we've been doing in Module 2 on particle statics. So we have an item that is relevant to the computations that we've been doing, and then how we express that item in both 2D and 3D. And I really like this table because it summarizes how much 2D and 3D are alike, not different. I would argue that the only thing that's really, really different beyond describing the vectors is how we express orientation in 3D. So in 2D, we can just look at it from a given angle. So we can just say, from the x-axis. That's why we have cosine and sine. In 3 dimensions, a more standard way of doing that is to use directional cosines. And directional cosines are really just the angle from the x-axis, from the y-axis, and from the z-axis for a unit vector. But we can look at the math and see that each of these terms are just the cosines of those angles. So if you have a unit vector, just take the inverse cosine of those constant coefficients, and boom, you have the angles from each of your x, y, and z axes. And that's all that I have on review. So that's pretty much it. That's what's going to be on the first exam. I formatted the exam such that, so it's all stapled together and there's like a problem per page. And so I formatted it in such a way so that, like, if here's the page, the problem's up here, so you should have ample room to write on the exam, and you could write on the back page if necessary. You should have ample room to solve the problem on the exam. I am going to have some scratch paper available in case some of you just have big handwriting. Like, I have big handwriting, I'll be the first to admit it. So if it's going to be a thing where you need more paper, you will have it. I will probably bring about 30 or 40 stacks of scratch paper, so like one set per student. I'll probably bring 30 or 40 of them because I don't think everybody in here will need it. But again, you can write on the front or the back as it's necessary. Okay, like I said, I was going to come in here for about 15 minutes and say, here's the deal with the exam. Now I'm going to shut up for a bit and I'm going to let you all start asking questions. If you all have any questions about format, about concepts, about homeworks, exams, example problems that we did in class, you can even ask me what the answer to number 1 is. I won't tell you, but you can ask. I want you to feel that you can ask whatever you want, okay? If I can't answer it, I will tell you, but if I can, I certainly will. The floor is yours. And now there's that point where it's like, who's going to ask the first question? Nervous. Yes?
So for like the short answer questions, do you think like it'll be like maybe like a definition or?
You can expect that. Okay, so the question was, for the short answer questions, can you expect a definition? Possibly. That's a very good assumption. It is possible that I also ask you a question about maybe a given scenario. I'll give you an example. So last year, I'll give you an example of what I did last year. So last year, I might give you a vector and I might say, like, just what's the y component? And based on the image, you should be able to see, oh, it's this or oh, it's that. But again, it will be very short. But definitions or questions about given terms, yes, totally totally a possible question.
For the 3D vectors, are you going to give us the axis, or like do we have to?
Yes. Okay. So the question was on 3D problems. Am I going to give you a reference coordinate system? The answer is absolutely yes, because I do not want to grade 8 different ways of doing the problem that are all correct. I want a single way of doing it, and I don't want that. I'm not trying to test you on stuff like that. I'm not trying to test you on stuff that's. I want this to be a statics exam, not a. Oh, let's speak. Oh, he did it that way. You know, that doesn't really matter to me. So yes, I will definitely give you the coordinate system on situations like that. How are you feeling about the exam? Are you nervous? Are you relaxed? I don't like it if students come in like this about exams. I want it to just be another day. Honestly, I just want this to be, oh, today we're doing an exam. It's just like coming to class any other day. Just we're doing stuff instead of Dr. Mike just rambling on for 50 minutes. So. Yes.
With the homework, the 2.5, the one with the 40,
Mm-hmm.
do you think we could go over one like that?
Yes. Do you want to go over that solution? Because I know that one.
Fine. That one is kind of confusing.
I knew that one was a little tough. I would argue that one is probably one of the trickiest problems we'll have all semester. And I'll also tell you that I'm not trying to trick you like that on the exam. I'll go ahead and tell you that. But I do want to go through that problem because I was sort of expecting that somebody would ask about 2.5. So let's see. So really the secret to 2.5 is this image right here. Well, maybe if the little dialog box. Okay, I don't care that much. Okay. So I think the secret to homework 2.5 is this image right here. Once you figure out this image, then the rest of the problem, the homework is pretty rote. So what we have is we have a scenario where there's a weight pulling down on the given spoke of a pulley. But the way that the pulley cables are sort of oriented, there's 2 cables going up this way and there's 1 cable going this way. So the way that you that you figure that out is you say that, okay, remember, we're using our samurai sword or lightsaber, our secret weapons of engineering here. So when I cut a section through this wheel, I'm cutting through basically 1 P here, but 2 P's here. So what I'm doing is I'm just describing these vectors, all 3 of them in IJ notation. The only thing is this is P and this is 2P. So once you figure that part out, the next steps then are as follows, okay? So if we look at the description of the vectors, so here's the free body diagram. We actually know what beta is. Beta is able to be ascertained from the definition of the problem because we know that this rope goes up 2.4 and over 0.75. So what we can do is we can write this 2p vector. Let me get this little menu here out of the way. we can write this 2p vector in ij notation where p is the only unknown. Whereas with the p vector, the goal of this whole problem is to try and determine p and to try and determine alpha. Okay. So once you get your free body diagram, again, like with any problem, the next step is to describe each of these vectors in ij notation, which you can see that I've done right here. So you can see I've got the 2p vector written in ij notation, the p vector written in ij notation, and the w vector written in ij notation. And remember, this is a 2D problem, so we should have two equations and two unknowns. And we do. The two unknowns are the letter P, which is the magnitude of that force inside the cable, and the angle alpha. Okay, so this one's a little different where I'm asking for an angle and a force. But again, those are two unknowns. Okay, so now that I've got my three vectors, the next step then is to add those vectors up in ij notation. Now, if I add up the x components first, what I've got is I've got this here plus this. The w vector doesn't have an x component. So what do we have here? Well, I notice that the p's cancel. So I've got the cosine of alpha equals 2 of this. So all I have to do is solve for alpha, and I get alpha as 53.38 degrees. Then I sum forces in the y direction, but with summing forces in the y direction, I now know what alpha is. So just plug and chug, and I get P is 723.58 newtons. So I know that that probably went kind of fast, but all I'm doing is I'm adding up the y components for each of those vectors, and I'm going, okay, well, I know what alpha is. So look at this remaining expression. I think I moved the 1962 over here. So what do I have? I can factor P out of that line. I get P. I get 2 times this plus that. Just divide by all that whole blue, and I get P at 723.58 newtons. So that's kind of the approach to that problem. And again, I know that that's probably the trickiest problem that I've given you during this module, and it will probably be one of the trickiest ones I give you all semester. So I want to stop for a sec. I rambled on. Did I answer your question?
Yes.
Okay, how about everybody else? Because sometimes I do that. It's all just to go on and on. It's like, wait a minute, I'm not actually addressing what you asked. So maybe, but not this complicated. In no way, shape, or form am I going to trick you this as much as this. So it is pulleys on the table, yes, but not this hard. So. Yes.
So I was looking on the homework, I think it was either the third homework and then the fifth one.
Mm-hmm.
It was actually asking about the direction of the resultant, and one
Mm-hmm.
answer was with an angle, and the other one was with a basic number.
A unit vector?
Yes, a unit vector. How did those differ? Is there like a question in the...
That's a good, okay, so let me answer that 2 different ways, okay? So if the question is how do they differ, I think there's not really a difference, it's just the way that you're describing the orientation. So in 2 dimensions, it's easy to just say it's an angle. Whereas in 3 dimensions, one angle isn't enough, which is why sort of a unit vector or those 3 angles is sort of necessary. Now, adding to that, let me give you my second answer. What I am not interested in is that type of ambiguity on the exam. So, for example, if it's a 3D vector and I'm asking for orientation, I'm going to tell you I want this, this, and this in, to such and such degree and so on and so forth. If it's 2D, I'm going to say I want this angle or I want this dimension, and I'll tell you I want it this, I want it in meters or feet, and I want it to, somewhat to this precision. Because I'm not trying to ask a question where you're like, I'm not really sure what he's after. That I'm really trying to avoid here. And I try to avoid that a lot in my engineering courses in general because I don't think that leads to safe designs. I'm serious. I would rather that if I was designing a bridge that I knew what I needed to design for, because that's the type of stuff that kills people if there's not adequate communication. So I'm not trying to trick you in that regard. That answer your question?
Yes.
Is everybody else okay with that? Okay. Because that's the other thing. When somebody asks a question, I want to make sure their question, that they get their question answered. But everybody else needs to understand what I say too. So. Yes?
Go over 3D equilibrium again.
I'm sorry, say that again?
We go over 3D equilibrium.
Sure. Let me ask you this. Would you like to review the example problem that we did in class or the homework assignment?
Either.
Let's do the homework assignment because that's new. We didn't talk about that. We talked about that problem in class because we were doing it together. Let's do the assignment. And this is homework 2.7, so this solution just became available. Let's look at that. Okay, now let me say a couple things about not just 3D, but I want to talk to you about how I grade in general, because I want you to understand my approach. Generally, I tend to use two approaches when I grade problems. The first is what's called a correct for data approach. So let me explain what a correct for data approach means. If you have a problem that takes 10 steps to solve, and you make a mistake on step 2, I'm going to deduct points for that mistake made on step 2. Not if the other steps are completely fine, okay? So I'll tell you how that goes, right? So let's say you have a problem on the exam. I will have an Excel sheet set up that computes, that goes through the solution for that given problem. And then I'll take your work, okay? If you got the same answer I did and you showed your work, it's right, move on. But if you're not getting the same answer that I did, then there's a mistake, okay? And what I will do is I will go through and I'll see, okay, what's the mistake? And if it's only this one value, and if I change that one value and I get the same answer that you do, then that's the only thing that you got wrong. So I'm only going to take off for this. So what the point I'm making is what I'm not going to do is take a look at my answer, take a look at yours, and go, oh, minus 30, it's wrong. I'm not doing that, okay? I'm going to go through and give partial credit as much as possible, okay? The reason why I'm going on about that is because I think the hardest part about 3D is this, the very, very first part, which is just defining the vectors, okay? I'm sure that there's going to be people that have an error on, let's say, the AB vector, and it causes the rest of the problem to have errors that cascade through it. My goal is to only deduct for that one error, not for the whole thing. You see what I'm saying? So what I don't want you to do is get worried, because I know probably the most difficult part about 3 dimensions is figuring this part out. And I don't want you to think that if you get a wrong value, that suddenly that's minus 35 points on the exam. I don't want you to feel that way, because my goal is to try not to do that. That's my approach when I grade, and I try and use that as much as possible. The other approach is if I'm looking at the homework or the work, and I generally don't follow any of it, I'm going to have to look at it and I go, okay, I kind of understand what's going on, minus 14 or something. I'm going to have to call it. I really don't like to do that. And sometimes I'm looking at the work and I'm having a hard time understanding it. But I really try and ensure that I'm being fair when I grade. So I know I went off on a tangent there, but I thought that was pretty relevant to talk about given the nature of this problem. Okay, so going to 3D equilibrium, I think that the hardest part is defining the distance vectors, because ultimately the first stage of the problem is to describe each of the resulting vectors in 3D, okay? Now, when you have vectors at an arbitrary orientation, like AB, AC, and AD, what you need to do is you need to first define those distance vectors in 3D. So for example, if I look at vector AB, and I know this is probably among the more difficult ones to kind of see, but I can look at AB and I can see, okay, from A to B, I go negative 450, okay? From A to B, I go up 600, and notice how they're all 600 in the Y direction, because here's the weight, here's the ceiling, it's all an elevation difference of 600. But in the Z direction, I do not change at all. Okay, so I've got negative 450I, 600J, 0K. Okay, so I do that for each of the 3 vectors. So I've got AB, AC, and AD. Okay, and now that I've got my distance vectors, I can take those distance vectors and use them to describe the force vectors. How do I do that? I take those distance vectors and I convert them to unit vectors by dividing by their own magnitude. So I compute the magnitude of each of those vectors using the Pythagorean theorem, and then I divide each of those vectors by their own inherent magnitude to yield these. These are unit vectors. Unit vectors have no dimensions, right? So it's just negative 0.6, 0.8, and 0, and so on and so forth. And then I take each of these vectors and I multiply them by their respective magnitudes in order to get the force vectors. Now, what we find in this problem is that I've got, here's TAB, here's TAC, here's TAD, here's W. So here's the vector IJK, IJK, IJK. Now, in this problem, what we were given, this is a 3D equilibrium problem, bless you. This is a 3D equilibrium problem, so we have 3 equations and 3 unknowns. While the 3 unknowns are a little different, the problem that we did in class, the 3 tensions were the unknowns. The one on the homework, we were given one of the tensions, and we've got to solve for the other 2 in the weight. In the end, it's 3 equations, 3 unknowns. So the very first stage of the problem is to get to this right here, where you have described each of those forces in IJK notation, okay? And so this is what I've got, all right? The next step is to then apply the equations of equilibrium. And so applying the equations of equilibrium means summing these components, and summing these components. Now, what we did in class is we took that resulting system and we wrote it in matrix notation and we solved it out. And I want to be 100% crystal clear that will work for this too. It will work. Nobody says it won't work. But I like to be an engineer about things, and I also like to be kind of lazy about things. If I sum forces in the x direction, what do I get? I get negative 0.6 TAB plus this equals 0. If I did that one first, I could solve for TAB, right? So you do this one first, and you find, by golly gosh gee, TAB is 4.167 kilonewtons. And if I do sum of forces in the z direction, I can do that one next and get TAC. So the only difference between what we did in class and what we did here is instead of just blindly plugging them into a 3x3 equation solver, I was just kind of smart about it in what order I did it in, okay? And so I sum these first, get an answer, then sum these, get an answer. Then when I look at sum of forces in the y direction, there are 3 unknowns. There's TAB, TAC, and W, but I already know what TAB and TAC are from the previous 2 expressions. So I have those values, plug them in, do some algebra, and I get, bam, W is 9.71 kilonewtons. And so that's sort of the process in general. So in 3D equilibrium, I think the first stage is to describe those forces in 3D. Now notice how I didn't write distance vectors and a unit vector and all that stuff. Notice how I didn't do any of that for the W vector. And I didn't do that because I think I can describe that W vector just by observation. Now I can just look at the problem and see that W vector is the magnitude pointing down times J, because here's the problem. What is the vector that represents this weight? It's whatever the magnitude is, negative that times J. That's it. The purpose for writing the distance vectors and then converting to unit vectors and then multiplying by the magnitude to get force vectors is to define those vectors whenever the orientation is not simple, whenever it's all over the place, okay? Does that make sense? All right. Now, I want to make sure I answered your question. How do you feel about that? Is there something we missed?
Mostly, once you get the IJK of what you were calculating, how do you go from that to the magnitude of the weight?
Are you, so what step are we talking about? Are we talking about,
Very last.
you're talking about right from here?
Like if you keep going down, how do you get W 9.7?
Okay, all right, let's talk about that. So before we talk about W, let's make sure, are you okay with these?
Yeah.
Okay, so I think the first question is how do I get the equation, the first line? The way I get the first line is I sum up the components in the y direction, okay? So if I sum up the components in the y direction, what do I get? 0.8 TAB, 0.8824 TAC, 3 kilonewtons, and negative W. So that first equation that you see is just summing up these components and setting them equal to 0. That's where I get that, okay? So before I move to the next line, are you okay with how I got this? Does that part make sense? If not, I mean, we can go back.
Yeah, it makes sense.
So here, yeah, maybe a good way of doing it. I'm sorry if this is kind of small, but I'm going to zoom out a little bit. So this equation right here is just summing up that column, right? Because, like, for example, if I sum up this column right here, that is the sum of the forces in the x direction. This is the sum of the forces in the y direction. This is the sum of the forces in the z direction. So, for example, if I sum up forces in the x direction, what do I get? Negative 0.06 plus 2.5 kilonewtons equals 0, right? If I sum up the z direction, what do I get? I get negative 0.4706 TAC plus 1.8 kilonewtons equals 0, right? So that's where this equation comes from. With me so far? Okay, now I look at this equation. So how many unknowns are in this equation? How many variables? I've got TAB, TAC, and then W, right? But notice how TAB I had already solved. I had figured that out from doing one of the earlier expressions. And TAC I had already figured out from doing one of the earlier expressions. So what I'm doing in the next line is I'm just substituting those in. So where it says TAB, I'm plugging in this. Where it says TAC, I'm plugging in this. Now, look at the equation. So let's look at it now. I've got a number times a number, plus a number times a number, plus a number minus a variable, right? So see this W is now the variable. So, but look at it from an algebra perspective. See how I got a number plus a number plus a number minus W equals 0? If I move W to the other side of the equation, well, by golly gosh gee, I've now solved for everything. So all W is just that, and if you do the math, you get 9.71. Did that answer your question?
Yeah.
Is everybody else clear about that? Because I want to make sure that's clear for everybody else here. And I want to be, again, clear about something else. If you were more comfortable with taking this system and writing it in a matrix form and putting it in your 3x3 solver, that will work, okay? The only thing that you've got to do, well, there's two things I would point out about that. The first thing you got to do is make sure that you write your unknowns in order in every equation. So it's got to be TAB, TACW, TAB, TACW, TAB, TACW. So that when you plug that in your solver and your calculator spits out X, Y, and Z, when it spits out X, Y, and Z, that you know that, okay, Z corresponds to W. That makes sense? The second point I would make is that because of the nature of this problem, if you go through using a 3x3 solver, you're going to get a lot of zeros, okay? Because you have these really simple expressions here where you just get TAB equals that. So when you plug in that 3x3 matrix, a lot of those terms might be zeros, but that's not there's nothing wrong with that. It's just that's going to happen because of the nature of the problem. Does that make sense? Okay, any other questions about this? And I want to make sure I answered your question. You good? Okay, how about everybody else? This is good stuff. I like this. We got. Yes, sir.
Like on the exam, do we need to like label every step like you did, or?
So that's a good question. Here's what I'm going to say. I'm going to say that when in doubt, show the work, because here's what I don't want to have happen. I want, if you do something wrong, I want to be able to deduct only for that and nothing else. I don't want to look at your work and go, he messed all this up, when really all it was this one value. And if you don't put it on paper, I don't know what's going on in your head. You know, I'm Professor Michelson, not Professor X-Man joke. I'm a dork, I know. I'm an engineer. Of course I'm a dork. But in all seriousness, what I'm saying is show the value, show the steps. Now, I understand it's an exam. I understand it's timed, and you may not have time to write every single little thing down. So I'm going to understand if you're going through things a little quickly. I'm going to understand if the work is a little sloppier. And like what I'm not going to do is like on a line like this, oh, you didn't write a KN for kilonewtons, that's minus 50 points. I'm not doing that because I understand it's quick, okay? I do think that, and while it's not, I'm going to get a little bit on my soapbox here, units are not as critical in this course as they will be in later ones. So for those of you who take Engineering 216, units are going to become a very big deal in there. And I find that in a class like that, if you do not write the units out, whether it's Engineering 216 or BME 302 for your biomedicals, when you're doing stress analysis, if you don't write out those units, you can really result in some serious errors. Here it doesn't matter so much because everything's in kilonewtons, so it's all copacetic. So I get if you skip a unit, I think I understand it's going to be okay. But if you don't, like, if you went from here, like, here's what I caution against, okay? If you just went, if you had written this out, okay, and you just went from here to there, to W is 9.708, in my opinion, you're gambling. If it's right, you got nothing to worry about. But if it's wrong, then I don't have any evidence for any of this. And I don't know where your mistake was. And so I'm going to look at this and go, dude, I guess that's minus 10 points, even though it might have only been minus 1 or minus 2 because there was a plus where a minus should have gone. You understand what I'm saying? That's what I want to avoid. So when in doubt, I would show the work. So.
Is our equation sheet 1 or 2 for 1 or 2 sides?
Both sides. Both sides. Yes?
It sounds dumb, but 8.5 by 11, is that like a notebook paper?
That's just like a copier paper.
Okay.
Yeah. Yeah, I'm saying that's as big as it can be. If you have a sheet of paper like out of this, like if you have one of these and you use this, this is smaller than 8.5 by 11, so you could fill that and that'd be fine.
Cool. Like,
8.5 by 11 is like what's in this, like just a copier. Yes. So that's a good question. What I would do primarily is focus on, if you're looking at terms, I would focus on the fundamental lectures, the lecture, like lectures 2 and lecture 3, and probably a little bit into lecture 4, because those 3 lectures were where we were setting the stage for what vectors are, what our classical motion, Newton's 3 laws were, and so on and so forth. I don't think you need to go beyond that, because I think everything beyond that was, let's take these definitions and apply them. But what I will tell you is I'm not going to ask you anything that's like, you know, what was this one term on slide 14? You know, what did I mean by the second bullet? I'm not doing that. So, I mean, these are very fundamental basic concepts. If you had a pulse and respiratory pattern, you saw what I was talking about. So, yes. I'm not going to ask you to like regurgitate an equation on the conceptual. I'm not going to ask that. There is a possibility that you may have to do a very, very small calculation on one of those, but I mean very small. And I don't really want to say more than that. But again, the conceptual questions are meaning to test your understanding, not your math abilities. They're really not. That doesn't mean that there isn't a little bit of math effort into it. That's not what they're intended to do. I don't think I can say more than that without telling you what the question is. I don't want to do that. Yes. So you can expect 4 to 5 conceptual questions and 2 to 3 computational problems. No more. And one of the things that I try and do is I understand some of these problems are super large. So for those problems, more often than not, I will either give you some intermediate values or only ask you up until a certain point because I know we're time limited. I know we don't have a lot of time. So the other thing, I will try and push the exam to like maybe 8:52 or 8:53. The only problem is we have another class that comes in here after this, so we can't stay too late. That's another point. What I'm going to do on Wednesday morning is first off, I think you should show up a little early. I do. As you come in, I'm going to start handing out the exams, but I'm not gonna let you start until 8 a.m. You know what I mean? So we're gonna have a 3, 2, 1, go, you know? And so that way everybody has a fair shake at the exam. So yeah. Like I said, I'll have scratch paper up here in case anybody needs it. Big question is, are you feeling good about the exam? Any outstanding questions? Anything that you're thinking about? I'm sure that as we talked about this, as you all are getting ready for the exam, you will probably have some questions that you think about afterwards. Make a post on the Teams channel. I'll try and reply and put it to everybody so that everybody sees the response. Try and keep up to date with that as quickly as possible. So that way everybody's armed with the information in real time. Sound good? All right, one last time. Everybody good? 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 All right, I'm going to pull up the QR code one more time. I will see you Wednesday morning, 8 o'clock. Best of luck. We'll see you then.